The other piece here is that this distribution turns out to be a normal distribution. So we're not only saying that the sample means on average have the same mean as the population, and we're not only saying that the sample means on average have a smaller variance than the original population, but we're also saying that the sample means will turn out to have approximately a normal distribution. And that is the central limit theorem. The central limit theorem says that as long as the variance in the original population is not equal to infinity, in other words, for any practical case, if we sample randomly and independently from the initial population, the distribution of the sample means, the values we'd expect to see if we repeatedly sampled, are going to follow a normal distribution. And it turns out that that's true even if the original distribution is not normal. The best way to show that is by simulation. I'd now like to go over the same concept, but instead of talking about 65 and 4 particular numbers, I want to put notation on it. I want to put the conventional notation that we use to talk about distributions with certain means and certain variances. So we've got the population. Suppose that population follows a normal distribution with mean mu and variance sigma squared, then this quantity here, this upper bound will be mu plus 2 sigma, and this lower bound will be mu minus 2 sigma. And we said that if we sample from that population and we make a histogram of the values we get, it'll look a lot like the sample. That's what we hope. And then if we think about the sample means that we would obtain if we repeatedly sampled from the population and wrote down the means that we obtained, those also should follow a normal distribution centered at the same place with mean mu, but with a much smaller variance. In particular, the variance should be sigma squared over n, where n is the size of the sample and sigma squared is the variance from the original population. So now we're saying that 95% of the time, the sample mean will be between mu plus 2 times sigma over radical n, the square root of the variance, and mu minus 2 times sigma over radical n. In terms of the notation we've been using, we're saying that y follows a normal distribution with mean mu and variance sigma squared. And then if we sample randomly and independently, y bar also follows a normal distribution with the same mean, but with variance sigma squared over n. The central limit theorem says that this right here will be true, even if this is not a normal distribution, even if this is any distribution at all. As long as the original population has mean mu and variance sigma squared, then the sample means will follow a normal distribution with mean mu and variance sigma squared over n. And importantly, that'll be a normal distribution.